Hello everyone, welcome to the class of ECE for 51. Today I will give a review for the final exam. Alright. Firstly, let me explain some general information about the final exam. Go to the here. Now is a review for the final exam. First one is about the exam. It will be a online exam, similar with previous midterm exams, but we will have 2 hours. 2 hours and just one attempt. Just one attempt. Alright. And it will be available on, let me see, it's a Friday, right? Last time we have checked the schedule. It will be on Friday. Friday, December 8th from 8 a.m. to 11:59 p.m. The exam will be available during this time, so the whole day of that Friday, and you have to submit it by this time. So you better start at 9, before 9:59, but that's too rush. Maybe you start before 9:30, or even in the morning or the afternoon. That would be better, right? Okay, so it's in the Blackboard, right? Online, you go to Blackboard, you can find the exam, then open it and do it. Yeah. One thing you have to pay attention is avoid to refresh the page when you start the exam. If you refresh the page, you have the risk the system, the Blackboard will think you are done. You you're submitting your work. All right. So yeah. So this one, and what else you have to know? Yeah, I think fine. You should already familiar with it, right? Okay. Now let's see the coverage. It will cover 2 parts. The first part is those covered by midterm exam. Midterm exam 1, 2, and 3. Right? We have 3 midterm exams. And then digital control. Digital control, we have sections 4.4, chapter 4, in chapter 4, the last section of chapter 4, and the whole chapter 8. No, not whole chapter 8. In chapter 8, I think we already discussed the sections, the first few sections, section 1 to section 3, 3.2. Yeah, not all of them. Okay, so this is a digital control. I also discussed something about the digital control in the matrix form, but that is not required in the exam. Okay. Yeah, this is a general thing. And if you have any more questions, you can reach me in the Zoom meeting. I will schedule a Zoom meeting in the Blackboard. Then you can come to me if you have any question during the next week. All right. Yeah, I will put the schedule in the Blackboard. Okay. Now we go to the materials of these 350. So we have studied several parts. The first one basically we need some math tools, right? We need a Laplace transform, we also need some Z transform. But most of the works we need a Laplace transform. Right? Z transform only for the digital control. We need a little. Yeah. And then we have something about the complex number. We need to know something very basically, right? Basically, you should know the a plus bj, how to write it as in the exponential power way, right? So you should know if you have these, how to write it in this way, or if you have these, how to write it in this way. Okay. It's related by the Euler's formula. This is rho times cosine omega plus j sine omega. Right. So rho times cosine omega is A, rho times sine omega is B. Right. This is for complex number. And we also need something related to matrix. Right. Matrix. For matrix, you should know how to calculate the determinant, the inverse matrix, maybe contain S in it, right? We need the Si minus A inverse, right? We need this one, inverse matrix. Determinant of, determinant is also for this one, right? Determinant of Si minus A. And for the similarity transform, we need the inverse matrix, right? We also need the inverse matrix, some inverse matrix of some matrix. Yeah, so this is math tools. Not too much. The most useful is the Laplace transform. So you need to know how to do Laplace transform, how to do the inverse Laplace transform. In the you need a partial fraction method. Right. Yeah, this is the math tools. Also, of course, you need tables. Both Laplace transform and Z transform, you have tables. And partial fraction, you also need partial fraction for Z transform, inverse Z transform. This is the math tool. And then second thing, we have the system, right? We have system. For system, we have several things. We can describe a system by the equation, differential equation in the input and output equation, right? And then we have transfer function. Then we have the structure. Structures we can use a block diagram. Or signal flow graph. Right. So you have structure. And then the fourth way to describe a system, we have the metric style. Say the state equations. Metric form. Right. So we have 4 different ways to give a system. And we also studied how to change between them. So like you have a IO equation, then you can have a transfer function, right? You can have a transfer function. And when you have a transfer function, of course, you can also give a differential equation. And also like the structure, you can have the structure, right? You can have structure 3. So from the transfer function you can give structure, and you have structure, you can also give the transfer function. here you need the gain formula, right? Gain formula. I will put it here. Gain formula. Gain formula. Gain formula basically is gain formula is for the structure. You have a structure, you can find the transfer function by gain formula. And if you have a transfer function, you can also use the gain formula to build a system so that build a structure so that structure can give you the given transfer function. Okay. 1, 2, 3. And also for the fourth, state equations. State equations. Okay, I put it here. State equations. Then when we have state equation, we can have the transfer function, right? We have a formula. Here we have formula that is y over r in S domain, or means u. It depends. Suppose r is the input. Here will be c si minus a inverse times b plus d. Okay. So if you have state equations in matrix A, B, C, D, then you can have the transfer function by this formula. And if you have the transfer function, how to get? Can you give the matrix form? Actually, you need both. You need to use 3 as a tool. Okay, as a result, we just need this, right? From here to here. You have a transfer function, then you can have a matrix line. And here we have several cases. We can have CCF, OCF, and MCF. OCF and the CCF, you can write them directly. Right? You know the transfer function, then you can write it. And for MCF, you need to do the partial fraction. You separate the transfer function as summation of several small, simple pieces, and each piece give you a kind of a subspace and combine together as a MCF. And among all the different kind of MCF, the special one is DCF. DCF, that's for matrix that A, B, C, D, that A will be a diagonal matrix. Okay. To find this DCF, you can use the eigenvalue, eigenvector. Right? Okay, so I put it here. Yeah. Okay, so by this way, all of them, if you know any of them, you can find another way to describe the system. Right? Yeah. Okay, so this is a different way to describe the system. What else about this part? Yeah. As for what is the gain formula, you should find. Suppose you know or don't know. If you are not so sure, you can put it in a formula sheet, or so for your convenience during the exam. All right. Then we consider, okay, after we have a system, then we'll consider how to find the output. Find the output. Find output. Actually, this depending on the way to describe system. So if you have IO equation, then you need to use Laplace transform. Right. Then you also need an inverse Laplace transform. You Laplace transform, then solve the equation algebraically, and then do inverse Laplace transform. You can have y of t equal to something. Maybe you need to apply the initial value. Right? This is one way. Then the matrix style. A, B, C, D. If you have these, then we have x of t will be phi t times x of 0 plus the convolution of phi t b convolution with u of t. Okay. You can write this as an integral, right, phi t minus some tau B U tau D tau. You can also write it in this way. Yeah, it's a convolution. And then y, we want to find y. Y is just C x t plus A B C D D U of t. Use the input. So you get x from here, then plug in here, you get what is y. You can also write this the longer, it's c phi x of 0 plus c, and this integration. Then you can also put c inside, and plus du. Right, you put c inside the integral. Then c times phi times b, you will have a single function, not a matrix. Phi is a matrix, n by n. Times b, you will have a column. C is a row. A row times a column, you get just a 1 by 1 matrix, right? Just one function. Then you can make it shorter. So I put c inside. Now, of course, you can also, or by Laplace transform and inverse Laplace transform, you can have y of t equal to something. Yeah, you can just like this. Yeah, just by Laplace transform, then solve it algebraically, find y of s, then inverse, you can have y of t. We also have a special case if we have transfer function. Transfer function is given. And suppose 0 initial. Then y of s will equal to transfer function times the input function, and then the inverse Laplace transform, you have yt equal to something. Suppose you have transfer function, and of course you need a 0 initial condition. Okay. So yeah, similar with here, we have 3 cases, 1, 2, and 4. I equation, transfer function, state equation. And different case, you have different way to find the output. Let's see how to find the output. And then we need to consider the 1, 2, 3. This is 4. This is the control problem. Control problems. First one, we know we have 4 goals, right? The stability, the tracking, CK, yeah. Tracking problem, and the type, and similarly regulation, right? Regulation problem and the type, and then the 1, 2, 3, and 4 are sensitive. So we have these four goals. You need to consider when you have a system, you want the system to be stable, or you want the system has certain kind of tracking type, or tracking with the steady state, steady arrow, some stuff, right? Or maybe similar for regulation. You hope your system, after you add certain control, make the system more stronger to against the disturbs, right? Like regulation. So you need a regulation type and steady state arrows, or the sensitivity steps. Yeah. So you should know how to do some related calculations about these. Stability, you need to use the poles, location of the poles, to determine whether it's stable or not, right? You have stable, unstable, marginal stable, 3 cases, right? And this one, you should know the definition, how to calculate. And for feedback part, you should know we have a shortcut. We have an easy way to find the type and the steady state arrow, right? Yeah, you can refer to the. We have a review for this part in which exam we have this? Exam 2, right? Exam 2 we have this part. Yeah, you are not so sure, you go back to that review, or check the textbook, you can find all the details about this. And the second thing, actually is also kind of a goal of the control problem. We can say it's a kind of specification, yeah, some values, some specification. We have some things like the maximal overshoot, right? Maximum overshoot and the peak time. Okay, this is a MP, this is a TP. Things look like this. So here's a TP and MP. MP is this distance, this value, from steady state to the peak value. Now you can also use a percentage, like for example, this is a 1, and here's a 0.3. You can think this is 3% to compare with the steady state. Here's a YSS, right? Here's a YSS. Yeah, maximum overshoot, and we have, for the prototype. For prototype, second order system. Now we have this concept in generally, but for prototype second order system we have formula. Formula, right? We have formula for this. Maximum overshoot and peak time, and also we have the which one? We have the like a setting time. Setting time. We have the delay time. Rise time. Right. Setting time is like here TS. After these, the output were almost equal to the steady state. Here's only 1%, right? Here's only 1%. And delay time, okay, here's the delay time. Like in that 0.5, here's a 0.5. And this is delay time, right? And rise time is also like this. So from 1% to 90%, right? Not 1%. It's a 10%. 10% to 90%. Then you have 2 times. The distance between these 2 times. This is a TR, right? This is TR. Yeah. Now for the prototype second order system, all of these we have formulas. Right? When you design system, there will be some like a requirement. Okay. And they are in time domain. We also have some more values in the frequency domain. We have the that one is a resonant peak, right? Resonant peak and the resonant frequency. This is a similar graph, but that is for the frequency response. Then this point, this will be F. Okay, say this is F, not F. Frequency is omega R, and the resonant peak is what's the notation? I forget. This is MR, and just maximal for resonant. Okay, MR and omega R, and then we have the bandwidth. Bandwidth, right? This point is a bandwidth. bandwidth, right? Bandwidth. What else? Okay, so this is the second thing for some specific values. Actually, we have more, like the steady state of the static arrow, steady state of the output, steady state of the state. Yeah, you can see they are also kind of specific values. Sometimes our design goal will be like make the y of ss equal to a certain value, something like that, or steady arrow ess equal to some value or lower than some value. Yeah, so you should know how to calculate these in different cases. For IO equation or for matrix equation, both cases we can calculate to find these, right? Yeah. Find them in both, in different cases. IO equation or matrix form. Okay, some specific values. What else we want to find? Yeah, I think that'll be all. Yeah. Then next we want to find okay, what else we can know? We have the delay values. Okay. All right, now we consider we have some method to control, to design the control. Okay, so that is the third one, method to design a controller. Now here most case we have two cases. One is for the IO equation, input-output equation. We consider feedback system. Like this. We have something here, then summation, then go to here. We have actually this will be the controller, and then the plant, and here's a HS in the feedback. We call this as a feedback sensor, or just sensor, yeah. Plus and minus. This is the plant. This is the controller, and this is sensor. And here might be we have something N of S. Here's the input. This is output. This N of S. What's the name? You can call it as like a filter. Filter, input filter. Yeah, you can call this as filter. Right? The input signal. Before you really apply the input signal, you give a filter. You give a filter on the input signal. Yeah. Then the key thing is this part. How to design this part. You want the loop gain satisfy certain condition, and those conditions might be like in maximum overshoot, maybe on the setting time, or maybe in a steady state arrow. But in a lot of cases, we can the problem can be stated as a question about the pole. Where is the pole of the system? Yeah. And so for this purpose, we have several tools. We have the Rulakers. We can use Rulakers to find the location of the pole. We have the bolt plot. We have the Nyquist plot, and you also have the Ruth table, right? Ruth table. You can use this to determine certain coefficient to make the system to be stable, right? Yeah, we can consider the other method for this kind of system. we have this method, for method, and for these three, we need a graph. So here we will pay more attention on this one. We understand it, understand the graph, understand it, understand the graph. To draw the graph, it is not really required that you can use the help of computer to draw it. But when you have like a root lockers or a both plot, you should know what is meaning of this plot, and then you can find related information. Related information, like you have both plot. Can you find the breakpoint or the marginal point? You have both plot. Can you find the gain margin or the phase margin, right? And for Nyquist plot, can you use the Nyquist criterion to determine the stability of a system? And also you can find the range of k to make the system stable, right? And also use the root table. You can use it to find the range of certain parameter k to make the system stable. Yeah, things like that. So you need to find related information. Yeah. Do I need a list here? Yeah, you can refer to the review for this part. This is for midterm exam 3, right? Exam 3, we have this part. So refer review. Review of exams 3. Right, you can have more details about this part. Yeah, this is a method to design something. Design something, right? You need to design something. You need like a feedback. You design that k, determine that k value. Yeah, and okay, this is a 3. Actually, we have more part like the compensator, the lead compensator, lag compensator, how to apply them, how to define them. I didn't put them in exam, but actually they are helpful. Or as another one thing important is like the controller with the PID controller, right? PID controller. PID controller. Yeah, how to design the PID controller. Okay, so these are for the I/O equations, and then we can also have, I say this is A, and the B for the also design problem. This is for the matrix form of system. This is A, B, C, D. We have 4 matrices to describe the system, right? There will be x dot equal to ax plus bu and y equal to cx plus du. For the design, we have 2. Basically, we have 2 things. One is for the let me see. One is okay. Let's see. One is for the full state feedback. Full state feedback. So we add, okay, this is 1, this is 2. We will add the feedback r equal to use this is the input, and u will be the input minus k times x. So add this one. So 1, 2, 3, 1, 2, 3 together. That is a feedback system. You can also give a graph. Things looks like A, B, C, D. This is the system. Here's y, and here's x, and x will times k plus and minus. Here's a u, here's r. So like this. Okay. Add a feedback. And the second thing is estimator. We will have x bar dot equal to a x bar plus b u, and y bar equal to c x bar plus d u. The x bar and the y bar, they are the estimator. X bar is the estimator of x, and the y bar is the estimator of y. And here we need to check the difference between y and the y minus y bar, and added it to the second equation. So this is 4 and 5. Okay, I'll say this one. 1, 2, 3 is the feedback system. Right. 1, 2, and 3 is feedback system, and 1, 2, 4 and 5 is the estimator system with estimator. Right? Yeah. And how to determine K and L? K and L. Similar. K is acre. Okay, use place of A and B and the pole, list of pole. You want the system, the feedback system has certain kind of poles. You list the poles in this P list, and then you just run this, you can have K. K, the answer of this K will be a column vector. Column vector, the size is same as X. And L will be place of A transpose, B transpose, and still we need a list of poles. Here it's also a transpose. So L is a row vector. L is a row vector, so I put T here. K is a column. K is a column. K is a column vector, and L is a row vector. Now you can use these two. Just run a MATLAB, you can find them. Now you can also use a formula, right? Yeah. Oh, this is a exam 2. Which one? I said this one is exam 3. Is this exam 3 or exam 2? Or 2? I forget. Yeah, you check those previous exams, right? Some early exam. This one will be exam 3. Okay. All right. So these are the how to design. We have some method to design, right? And of course, other than these two, we also have the method like we can have a feedback based on estimator. And we can also have the estimator with reduced dimensional. That means sum of x is vector, right? x1, x2, xn. Some of these x is open to you, so you can have the value directly by observe or measure it, and some others are hidden. Then the estimator, you only need to estimate those hidden state. Some states are open, you do not need to estimate them. You can find the exact value by direct measure, right? So in that case, how to design the estimator, right? Yeah. But I think I didn't list them as the exam problems here. So in the exam, you know these 3, they will be fine. Okay. And then that is 1, 2, 3 method in design. Okay. Then the You can think this is also kind of a method to design a controller, but this we give a different part. We call this is a digital control. The basic thing is like we have some transfer function. This g of s, maybe it is a whole system, or maybe it is a part of a system. Like this is a you have system, you have several parts, and some part of it you want to realize in digital way. So you can work like this. So you do a from analog to digital convert, and then you go to a G, digital G. Now it's a transfer function on the Z domain, right, by Z transform. And then digital to analog again. You have, okay, the input is the same. Input is same, U of t. And after that you get, here's a U of n, ud of n. And here you have a yd of n. And here you have y bar of t. And here's y of t. So we want to find gd so that y bar t is close to yt. Things like this. And here we can give more details. This one we can suppose like this, or like y of nt equal to yd of n. Right? This yd of n. Yeah, you can think we want yd of n are symbols of y of t. Yeah, here the ud of n are symbols of u of t. Here ud of n equal to u of n t. T the step of the sample. So the basic thing, the basic problem is like this. So actually here you cannot think this is design of a control. Like you have a system, you want it to be stable, then you can select some, this is the controller, you select some controller. After you select that controller, you try to realize it as a digital one. So when you do this step, you will not take care about what is the role of g of s in the system. You just try to change this system to be digital. That's it. Yeah, you do not pay attention on the role of g of s in the whole system. Right? You just change this part, realize this part in digital. Yeah. Okay. Now the method to do this, we have actually we introduced three methods. One is the testing method. Right? Testing method. We will change all s to be 2 over t, and here's a z minus 1 over z plus 1. You just do this transform. We call this is a bilinear transform. So you change all s to be this one. Then the given transfer function by this transform will turn to be a transfer function on z. Yeah, in z domain. So you can have like g of s will go to g d of z equal to, I denote this as this sd. It will be g of sd. You just replace s by sd. You can have gd. Now the variable is z. Yeah, this testing method. And the second method is a matched pole and zero method. So here every pole or zero, like you will have a factor like this in the transfer function, you will change this to be z minus e to negative a t, the symbol step. Just like this. Change this, replace this by this one. And then you need to add some s plus, not s1, z plus 1. Z plus 1, some factor, some maybe some powers on the numerator. numerator in case if it's necessary. It is necessary. Remember how to do this? You need to make sure the result transfer function, the numerator has order as same as the denominator. If numerator has a lower order, you need to add some z plus 1 until numerator has same order with the denominator. And okay, then you also need to determine the k, right? Use g of 0 equal to gd of z equal to 1. Use these to determine k. Right? You also determine the k, where gd of z were equal to k times s minus some e to some 0 t, and denominator is s minus e to some okay, if it is 0, just plus. It's a plus some pi t. If pi are poles and zeros, just like this. Here's a k. How to determine k? Use this formula. So this is the MPZ method. And another method, it is a modified matched pole and zero method. For this one, yeah, almost the same, similar with MPZ, but the order of numerator were equal to the order of the denominator minus 1. Okay, so here will be the order of numerator were equal to the order of denominator. Okay. This is one less. Yeah, all these things like this. All right. Okay, there we are. Right? The last part, the digital control, and or the previous part, actually we already go over them in the previous exams. But today's review, I combine some together. Right? I gave them in a different frame. Consider we have the tool of the math tool, then how to describe a system, what are the basic problems, and how to design the controller, right? So we have different frame about the knowledge. Yeah. Okay. And if you have any more problem, you can contact me during the Zoom meeting. Join the Zoom meeting. I will give the schedule in the Blackboard about the Zoom meetings. Okay. All right. See you next time. That's all for today's review. Okay. Bye bye.